In this video, we'll begin our discussion of section 13.5. This is the chain rule for multivariable functions. What I'm going to do is talk about a few things from Calc 1, and then we're going to use an example to come up with the formula for our chain rule. Okay, so from Calc 1, recall that the chain rule worked like this. We could take dy dt, and we could find some middle variable x that relates y to t. So a couple notes I want to point out here. It says even though there are three variables x, y, and t in this chain rule, there is only one independent variable, t. It may feel like x is independent, but x is not. X is called an intermediate variable. It's actually not dependent or independent. All it does is give a path from y to t. So our dependent variable is y, our independent variable is t, and then we came up with an intermediate value x to relate the two. All right, we're going to use this idea. So notice down here, this is exactly what we've been working with. We have some function of x and y, right? So here's our new three-dimensional, right, function that we're going to work with. Then we also have these functions here. This relates t to x, and then this one relates t to y. So if I was trying to find a derivative, dw dt, there's two ways I could approach this. The first one I'm not going to do, but we could talk about. I could just replace x with this. I could replace y with that. Once that's in there, take the derivative with respect to t. Now on a test, I'm going to ask you to do it the other way, using the formula, or both ways, or to show two ways. Usually that's how I make you show both ways. So make you use the formula and not just plug in x and y with the t's and take the derivative. Okay, so let's get through this problem. We are going to, let's identify a few things, right? X and y are our intermediate variables. They connect t to w. T, in this case, is the independent variable, right? This gives two paths from w to t. So they want us to find dw dt. I'm going to do this really rough idea of, we'll call it a proof. It's really not. But maybe more of a discussion of how this is going to get us to a formula. So I'm going to write out some statements here, and I want you to think about them and write them down as well and think, do you agree or not? Right? As t changes, this is called delta t, right? Change in t. The x and y, when t changes, right, here and here, x and y respond by changing also. So we'll write by changing also. These are called change of x, delta x, and change of y, delta y. Right? And both delta x and delta y cause a change in w. And that's called delta w. Right? Hopefully that makes sense. As t changes, x and y change. As x and y change, w changes. Right? It's kind of that's the whole point of the chain thing, right? It's chained one thing to one and then the other. So let's write out a formula that makes sense here. The amount w changes is based on, and we just said this, the amount x changes w. If I take that amount and I add it to the amount, we only have two variables, the amount y changes w, that would tell me how much w changes, right? If I took the two things that affect w and I take up the amount that x changes it and the amount y changes it, and I put them together, that would tell me my total change in w, right? We can rewrite this in a different way. It's an amount that changes. So this is, we can find this. I'm going to write it out and then it'll make more sense. So it's the rate of change in x direction times delta x. This is a d equals rt type idea. right? The total distance or work move done is a rate times a time or distance, this delta x. That's how much distance has went past, right? So we don't need that, but we can think of it as taking a rate times how much we went past, and that would tell us the amount we need. That would be the amount x changes w, right? The rate it changes, how long did it go for? Also here, the rate of change in y direction, if I take that rate and I times it by delta y, that would give me the amount of y changes w, right? The distance y changes. How much y did we go past and what is the rate that it goes? If I take those and multiply them together, I get the amount that it actually changes. Now we're going to relate this back to math stuff. The rate of change in the x direction, we just learned that is the partial of w with respect to x times delta x, right? The rate of change in the y direction is partial of w with respect to y times delta y, right? And then we get down to our last, close to our last thing. I'm going to add a page. Sorry if you're at the bottom of yours too. Notice that there's no t in here, and we have to relate everything by t. So what we're going to do is divide both sides by delta triangle. So delta w over delta triangle, t. It's a triangle because of delta t. Then we have the partial of w with respect to x times delta x over delta t, plus dw over, or the partial of w with the with respect to y times delta y over delta t. Let me add a page to this because we're not done. Let's do it here, actually. Cool. All right, so we're there. Okay, I do want to remind you of something, and maybe it's been a while, maybe you're not seeing it this way, but let's make a note here. So recall that the limit as delta t goes to 0 of delta a over delta b is the derivative a with the derivative with respect to b, whatever that may be. The derivative of a with respect to b. That's what this is. This is the definition of a derivative, right? The change of a over the change of b, and then we let the delta t, the distance between the two, go really small. So keep that in mind. So if that is the case, if I let delta t, so letting delta t go to 0, all right, we get the derivative of w with respect to t equals the partial of w with respect to x times the derivative of x with respect to t plus the partial of w with respect to y times the derivative of y with respect to t. This is our chain rule formula. That is it. Okay, so a couple things. Notice we have partials and actual derivatives. You have to keep these straight. The way I keep them straight, it makes sense that if I was going to take some type of derivative of w, since w is made up of x and y's, it makes sense to me that I would need to take a partial, right? That's what I'm talking about here. Partial of w with respect to x, partial of w with respect to y. Well, if I go back and I look at my y, let's write those equations down. I'll do it right here. So w was x squared minus y squared. X is t squared plus 1. And then y is t squared plus t. Well, if I'm thinking about what's highlighted there, this is w. W is in terms of x and y, which means when I take the derivative, I have to make a decision. Am I doing it with respect to x or respect to y? So it makes sense that with those derivatives, I'm going to get a partial and not an actual derivative, full derivative. The other ones, this dx dt, this is an actual derivative. Notice that x and y are both just defined by one variable. They both have t. There's no x and y. So it doesn't make sense that we need to make a decision for a partial. We can just do the straight derivative because there's only one variable. Okay, so we need every bit of this. So I need the partial of w with respect to x, right? That's 2x. The partial of w with respect to y, that's negative 2y. I also need the derivative of x with respect to t. We get 2t. And then the derivative of y with respect to t is 2t plus 1. We can find our derivative now, dw dt, to be 2x times 2t plus negative 2y times 2t plus 1. There is my derivative. We would multiply that out, dw dt, 4xt, and you may be wondering, hey, we have a bunch of different, letters here, y, t, and t's. Okay, well, we could fix this if we wanted to. I could just take each part. I'm going to do that, dw dt, and I'm going to replace, okay, well, I know x is t squared plus 1 times t minus 4 times, okay, y is t squared plus t times t minus 2 times y is t squared plus t. I'm going to leave it there. We could simplify that down. Let's just leave it alone for the sake of time in the video. But we could pick a t now to plug in. I don't know if this had a t to plug in or not. I don't remember when I wrote the example. I did not. Okay, there is one with a t. So the important part here that you need to have is that is my chain rule definition for dw dt. Okay, let's get another example, and I'm going to show you another way to think about this. I'm going to draw this diagram. So here's my main function. So main function. Then I'm going to put my intermediate variables, intermediate, and then also the independent variables. So I have 3 different spots. This is what I write. Okay, so w is my main function. My intermediate values in this problem are x and y. And then my independent in this case is t. And what I do is I connect them. Just like this. This is a plus. And this is how we can come up with our formula. If we want dw dt, we're going to need, okay, this is the partial of w with respect to t times the derivative of dx dt. This one is the partial of w with respect to y, not t on that first one if you're wondering why there. This is with x. There we go. And then we get dy dt. You can memorize it that way, use this diagram. This is going to help with extending this idea here in a moment. But that gives me my definition. dw dx times dx dt plus dw dy times dy dt. There's my formula. Okay, so we need each part of this. So let's scroll up. We can see it at the top of the screen. I need dw dt. It's the first thing we're going to find. Right, with the partials, right? And it's not t, it's x. I did that twice now in the same problem. Partial of w with respect to x. So w is there. We get 2xy minus y cubed. I'm also going to need dx dt. I'm just going to put them right next to each other now. Derivative of cosine t is negative sine t. We also need the partial of w with respect to y. I'm looking back up at my function. Okay, I get x squared. Looking back up, minus x, y cubed, I get minus 3xy squared. dy dt, y being e to the t, this was just e to the t. So dw dt is equal to 2xy minus y cubed times negative sine t plus x squared minus 3xy squared times e to the t. So there is my derivative. They want us to plug this in, dw dt. We use this notation because we're going to have multiple things. They want us to plug this in when t was equal to 0. If t is 0, we can find x and y by plugging it in right here. So if I plugged a 0 in there, x is cosine of 0, which is 1. Okay, so I'm going to write that down here too. X is 1. And then I'm going to figure out what y is. It was e to the t. E to the 0 is 1. So both of those are 1. This allows me to plug everything in now. 2 times 1 times 1 minus 1 cubed times negative sine of 0 plus 1 squared minus 3 times 1 squared times e to the 0, which is 1. This ends up being a negative 2. So that means that w changes with respect to t. For every t that gets moved, my w goes down 2. That's all that means, right, at that time. Okay, we'll stop this video here. We're going to work with expanding this topic in the next video, and then finishing up with expanding this idea to a new formula.